Welcome. I am Garima Tripathi, taking the lecture 38 on spectroscopic techniques in phytochemistry, UV and IR. Spectroscopy. The isolated and purified plant constituent should be identified and its chemical nature has to be determined. The plant compounds could be identified by their spectral characteristics. Spectroscopy is the use of absorption, emission or scattering of electromagnetic radiations by the atoms or molecules or atomic molecular ions to qualitatively or quantitatively study the atoms, molecules or to study the physical process of a compound. Illustrating the terms absorption, emission or scattering are the properties of light. When the light or the electromagnetic radiation reaches a sample, some amount of the energy from that is absorbed by the sample and the lesser energy radiations are released. So, this is termed as absorption. Similarly, when the electromagnetic radiations reaching to the sample are reaches the sample, a higher kilocalorie per mole energy is released, is called as emission. That means, here the energy, more amount of energy was emitted. Then comes scattering, which is of two types. Once the electromagnetic radiation reaches the sample, there is possibility two types of scattering occurs, either in or out scattering. So, exploiting this principle of the light or the electromagnetic radiation, the physical identification, spectral characteristics or chemical nature could be determined. So, theory behind the spectroscopy is mainly the interaction of radiation with the matter and its effect. It can cause either redirection of the radiation or transition between the energy levels of the atoms or molecules. As already known that atoms and molecules are having various energy levels for the with the subatomic species like electrons, protons, etc., and the either redirection of this energy or transition between these various energy level will lead to the spectral changes. This transition could be as absorption, emission or the scattering effect. Among the number of spectroscopic methods, ultraviolet absorption or UV visible absorption, infrared, that is IR, NMR, that is nuclear magnetic resonance, and mass spectroscopy, that is MS, plays a crucial role in identifying the plant compounds. Ultraviolet visible absorption spectroscopy. Different organic molecules with certain functional group called as chromophores that contain valence electrons of low energy level can absorb the ultraviolet or visible radiation at different wavelengths. So, here chromophores are the functional group that are capable of giving some color. So, hence termed as chromophores. So, these chromophores can give color because of various valence electrons which are capable of low energy and can absorb these either visible range or UV radiation at different wavelengths. Hence, the absorption spectra of certain molecules will show number of absorption bands corresponding to their structural groups within the molecule. Most commonly used solvent for the sample preparation in UV is 95% of ethanol because it is capable of solubilizing almost all class of compounds. Other solvents used are water, petroleum, hexane, ether and methanol. So, absorption is recorded using a detector such as photodiode array, that is PDA. This phenomena could be used to identify various functional groups of certain molecules, or when PDA detector is connected to HPLC system, it could be used to monitor the separation or purity of certain mixtures or compounds that contain different chromophores, that is the molecules having functional group capable of giving certain color. The nature of chromophore within the molecule, while the compounds possess chromophores are detected between 200 to 700 nm, that is the visible range, and others which do not possess these chromophores are detected under UV of 200 to 400 nm. So, let us give a light on the type of range of radiation. UV is the shortest wavelength containing rays, then we have this visible, and then we have this IR. So, this is the electromagnetic spectrum. UVs are known to be of short wavelength, while visible range in the range of 400 to almost 700 or 800 nm, and the IR is still longer wavelength, possessing more than 800 nanometer wavelength. And these chromophores, as already mentioned, these chromophores will get excited. Let us have a brief little more discussion on the type of excitement which a chromophore will encompass. So, there are many transitions from the electron at the electronic level. The most common and the most large energy taking transition is from sigma to sigma steric. Then we have the transition to n to the pi steric. We have transitions from the pi bonding to pi anti bonding. And n to sigma steric. These are the various transitions of the valence electrons. So, here is the schematic diagram or the instrumentation of ultraviolet visible spectrophotometer. So, it includes a light source, a monochromator which sends the selected selected range of wavelength. There is a sample holder where the sample is mixed with the solvent, preferred solvent, which is generally 95% of ethanol. Other solvents could also be utilized. Once the light is passed through this, absorption takes place and the transition of the electrons takes place, and the emitted light is then detected using the detector, and all the transitions are recorded in UV. So, on this detection of the wavelength of the compound, the study of functional group or chromophore could be extended by observing the type of shift in the wavelength. So, there are two types of shift. The graph is plotted where y axis has absorption and the wave length is shown on the x axis. The maximum, this is termed as lambda max. So, any shift in the blue side suggests that the wavelength has shortened up, and it is termed as hypsochromic shift. Short and blue. On the other hand, red shifting is bathochromic shift, and here the the wave gets shortened up. Okay. So, compounds absorption spectra can change with the change in the solvent in which the compound was dissolved. The value of UV and visible spectra in identifying unknown constituents is obviously related to the relative complexity of the spectrum and to the general position of the wavelength lambda max maxima. So, ultraviolet visible absorption spectra, a variety of natural product of pharmaceutical significance are analyzed by this spectroscopic technique. For example, lobeline, a constituent of Lobelia inflata, shows 249 nm lambda max. Then we have reserpine, used as anti-hypertensive drug extracted from Rauwolfia serpentina, shows the absorption at 268 nm. Morphine, the opioid analgesic alkaloid, showing the lambda max at 286 nm. Cardiac glycosides 217 nm absorption at lambda max absorption. Similarly, colchicines at 360 nm. There are certain other phytoconstituents like the range of coumarins. These class of compounds are naturally very fluorescent, and they give they can be easily identified by the UV absorption spectra. The phytoconstituents that could be analyzed in the visible range are alkaloids of ergot, that is 550 nm using para-dimethylamino benzaldehyde. Then we have this morphine in visible range will be identified at absorption spectra of lambda max with 442 nm by nitroso reaction. Anthraquinones will have lambda max at 505 nm after the treatment with alkali. Cardiac glycosides will show the absorption max lambda max at 590 by the Keller-Kilani reaction. Then cyanogenetic alkaloids will show the lambda max at 630 nm by pyridine pyrazole color reaction. Next is infrared radiation or spectroscopy or infrared spectroscopy. So, this is done by IR spectrophotometer, and again the plant compounds used is either in liquid, that example chloroform, as a mul or eugenol oil, or in the solid state mixed with potassium bromide or KBr to form a thin disc, and then this is kept in the spectrophotometer and the study is conducted. The term infrared covers the range of electromagnetic radiation between 0.78 to 1000 micrometer, or as already mentioned above 700 nanometer. In context of infrared spectroscopy, wavelength is measured in terms of wave numbers which have the unit centimeter inverse. it is useful to divide the infrared regions into 3 sections: near, mid and far infrared. So, near infrared has the wavelength in from 0.78 to 2.50 and the wave number as such. Then middle in IR is from 2.5 to 50 nm, while far one is from 50 to 1000 nm. So, these three types of infrared radiation is capable of performing or different type of excitement, like in this region the overtone or combination of the molecules are excited. The molecules get excited, overtone, and combination of molecules we can find vibration. In the second one, the study of fundamental type of vibration takes place, like rotational and vibrational. Excited, overtone, and the last one is the feeble one, where the rotational spectrometry is observed. Here is the schematic representation of IR, where IR source is there. The sample is kept either in the disc form with KBr or in the liquid form in eugenol oil and other mentioned solvents, and then the detector is kept to observe, which observes the emitted radiations. Processor displays the reading. The most useful IR range lies between the 4000 to 670 centimeter inverse. The IR radiation does not have enough energy to induce electronics transitions seen with UV. So, absorption of IR is restricted to compounds with small energy differences in the possible vibrational or rotational states. For a molecule to absorb IR, the vibrations and rotations within a molecule must cause a net change in their dipole moment. So, the instrument identifies the change with respect to the change of the dipole moment of the molecule. The alternating electrical field of the ratio of the radiation interacts with the fluctuation in the dipole moment of the molecule. If the frequency of radiation matches with the vibrational frequency of the molecule, then the radiation will be absorbed, causing a change in the amplitude of the molecular vibration. IR spectrum is the most simplest and reliable tool because many functional groups can be identified by their characteristic vibrational frequencies. It has a role in structural elucidation, in particular with the new compounds in the plants. The atoms in a CH2X2 group commonly found in the organic compounds, and where X can be represent any other molecule, can vibrate in 9 different ways. 6 of these vibrations involve only the CH2 portion. That means 6 of these are CH2 portions of vibration. 2 stretching modes, like stretching modes are again of 2 types, one symmetric Vs and another is the anti-symmetric VAS, and 4 bending modes, that is scissoring, which is written as delta, rocking as sigma, wagging omega, twisting tau. So, these are the various vibrational moments. Here we can see the radial movement, symmetric stretching, that means in the similar direction the stretching is taking place. Anti-symmetric stretching, that means in the opposite direction the stretching is taking place. Then we have this symmetry directional latitudinal. So, in this direction either it is scissoring, that means like scissors it will go apart and come nearby. Then this is rocking, that means both the ends are moving in the similar direction. Then we have this symmetry directional, again longitudinal. Wagging means coming front and back. So, this movement is called as wagging. And then there is twisting, that means coming front and back in a different not in the similar direction. So, this is termed as twisting. The widespread use of IR spectroscopy for the identification of drugs like polymorphic modifications, excipients and raw materials used in the pharmaceutical manufacturing is due to its sensitivity and ease with which spectra can be obtained on any type of sample, including insoluble solids, polymers, solution and gases. So, this gives an advantage of IR in the usage of this spectrophotometer in pharmaceutical researches or manufacturers, as they are capable of identification of drugs, are capable of identifying polymorphic modifications, are capable of depicting the excipients, raw materials used in during the pharmaceutical manufacturing, etc. So, IR spectra of two samples is very good evidence that the samples have the same chemical structure. So, IR is a good tool for detection of functional groups of biomolecules, thus aiding in their structural elucidation. The quantitative analysis of antibiotics, alkaloids, quinine, strychnine, steroidal sapogenins, etc. is possible with IR. And recapitulating the concept of spectroscopy with the aid of UV and IR, we will follow the first simple concept, that UV visible absorption spectroscopy ranges from 200 to some 700, where the visible range is from 400 to 700 nanometer, and the absorption or transition of the energy level leads to the absorption and shifting of the wavelength. This is due to the functional groups or the chromophores which are capable of giving color. The shift could be either bathochromic or hypsochromic. Batho means shortening of the wavelength, while hypsochromic means longing of the wavelength, and change in these wavelengths are suggestive of the type of or the structure of the natural product. Some examples were described here: lobeline, reserpine, morphine, cardioglycosides and colchicines. Every of these molecules ranging in the wave length of 259, having a lambda max of having an absorption at the lambda max 249 nanometer, 268 nanometer, 286 nanometer, 217 nanometer and 360 nanometer. Next was IR, where the IR was divided into three regions: near, middle and far. So, the near ranged from 0.78 to 2.5 nanometer, middle from 2.5 to 50 nanometer and far from 50 to 1000 nanometer. The unit that is commonly used for the IR spectrum is not the wavelength, but it is the wave number in centimeter meter inverse. So, the first near infra gives an excitement of complete vibrational overtone to the molecule or the complex mixture. The middle one shows the intermediate rotational and vibrational change, while the far infrared shows mainly of it is of low energy and it shows the rotational changes. And here we there are various type of vibrational and transition. This the dipole moment of the molecule change on the exposure to the IR. So, change in this particular dipole moment is recorded and it will give various modes of vibrations. One is stretching mode, which could be symmetric or asymmetric. Then are bending modes, which is scissoring, rocking, wagging and twisting. And here are the all types of vibrations: scissoring, rocking, wagging, coming to and fro, twisting. And with this I wind up the topic of IR and UV spectrometer. These are the references: SL Dore, Biren Shah, CK Kokate, as well as the pick courtesies from Wikipedia. Thank you.